Hello everyone, welcome to our channel. I'm Rucha Tambe. Today we are going to have a demo for linear regression with validation dataset. We are going to use the same California housing dataset which was used previously. Let's get started with the demo. So first, I have performed certain import, like I've imported pandas, TensorFlow, Matplotlib, and so on. Here you can see there are two new libraries. From Matplotlib import CM. This is used for plotting a good color map to find a good 3D representation or a good visualization of your dataset. The reasons could be various. For example, if you want to represent a form or metric data, or you want to understand your dataset better. Another important library which we are using is the grid spec. It specifies the location of the subplot in the figure. We'll see how each and everything is done in the later parts of this video. Now, another thing we have done is we have set the logging to error, hence it will display only the error messages. We have loaded our training data, California housing train, into our data frame, California housing data, and we have described and printed the first 5 rows of our data set to have a better understanding of what the data is actually. So it shows me the count of the rows in the data, which are 17,000. There are 17,000 entries, each having features longitude, latitude, housing median age, total rooms, total bedrooms, and so on. And the label which we are predicting is the median house value. Now, as a recap, in the previous video, we have seen that we have used a single feature to predict the median house value. In this particular demo, I'm going to use all of these features and some other additional synthetic features to arrive at a prediction of a median house value. We will also see that this gives you a better accuracy and a lower root mean square error as we proceed. So why do we need to create synthetic features? When you train a classifier on a data set, it happens often that you are stuck with a certain performance and are unable to get past this performance. Which means, for example, if I have an 80% accuracy, and even after adding new training data or using a complex model, I cannot increase the accuracy of my model much more than 80%. I am stuck at a value. So what we can do is we can use the existing features like the latitude, longitude, etc. present here and modify them in such a manner that there are some additional features added to your data set. In this case, we'll define a function called preprocess features, which is going to do a similar thing. I'm going to create a new feature called rooms per person by dividing the total number of rooms by the population of the data set which I have. So let's do that. We are moving to this first step, preprocess the features and labels of my data set. So for that, I'm going to define a function called preprocess features, and I'm going to pass into it a California housing data frame which we have created earlier. Now this function is going to return a data frame called process features, consisting of features to be used for the model, including the new synthetic feature which we are creating. So first I'm going to create a variable selected features, and I'm going to enter all of these features except the last one, median house value. Let's say I have the longitude, I have the latitude, I have the housing median age, I have total rooms, total bedrooms. This is basically all the features which we are using to predict our label, which is median house value. Household median income. Right. Now we are going to create another variable process features and copy these selected features from the data set using the copy method. And finally, I'm going to add a new feature into this processed features. How am I going to do that? Using the array subscript rooms per person. This is my new feature, and I'm going to obtain it by dividing the total rooms value by the population value. So we are going to access the total rooms column using the subscript notation again. California housing data sub of total rooms divided by California housing data population, and finally return this data frame process feature. Right. So we have processed our features. We are also going to process our target value or our labels, and we are going to divide each row by 1000. So we have a function for that. Reprocess target California housing data, again passed as a parameter, and this feature is going to return me a data frame with all of its entries divided by 1000, and this data frame is containing entries of the median house value column. So pre-processed targets is a new data frame which I'm creating using pd.dataframe constructor, and in that again in a similar fashion I'm going to modify the existing column median house value by dividing each entry by 1000. California housing data median house value by 1000, and then do not forget to return this data frame. Reprocess targets. Alright, now we move on to the next feature, split into the training and validation datasets. Right now, for demo purpose, I'm going to use the first 12,000 examples of the 17,000 which we have for training and the last 5,000 for validation. And for each of these entries, I want to pre-process these features because I want to add a feature called rooms per person for each of this training and validation data. And I also want to pre-process the targets by dividing it by 1000. So we are now going to call these functions pre-process features and pre-process targets for the first 12,000 entries for the training data, and then for the 5,000 entries for the validation data. Now let's do that. Let me call this function pre-process features, and in the data frame I'm going to now pass the first 12,000 entries. But using the head function I'm passing the argument as 12,000, and this is going to return a data frame. Let's call it training examples, and let's see if we are getting the correct values. Describe. Yes, so we can see the rooms per person value is added, and the maximum value is 55 and the 75th quartile is 2.25. Now let's pre-process the targets for these 12,000 values because we also want to divide the targets or the labels by 1000. So let's call the function pre-process targets and pass the first 12,000 entries and catch this in training examples, training targets, let's say, because examples variable is already used, training targets. Let's describe. Now we are going to do a similar thing for the validation data. The only difference would be that we would be calling the last 5,000 rows. So for that, we are going to use a tail function and pass 5,000 as the parameter here. So let's do that. Let's call this validation example. And we change this because we are going to pass the last values, last 5,000 values, and describe the validation example. Similarly, for validation targets, and have a tail of 5,000, and again describe them. Cool. So we have now obtained a split of 12,000, 5,000 for training and validation. Now, let's have a plot, or let's examine this data and visualize the training and validation data sets. For this, we are going to use the matplotlib library. So first, let me create a figure of figure size equal to 13, 8. And I'm going to use a subplot function. What this subplot is going to do, it's going to divide a single area, this area I have, into multiple subplots. Why am I requiring this? Because I'm going to visualize my validation data here, and adjacent to it, I'm going to visualize my training data. So a single area is getting split into two columns, and each column has its own plot. This is why we are using the subplot function. It accepts three parameters. So right now we want to create two columns of a single area. Hence the second parameter is 2. And first we are plotting the validation data here. So the first entry or the first column is going to have the validation data. Hence right now we are going to provide this third argument as 1 and store it in a variable, say AX. So this is why we are using a subplot. Now filling the first column of the subplot, I want to set the title of the first subplot to validation data. And I'm also going to set the Y limit and the X limit. So to plot this data, we are using the two important geographical features of the latitude and longitude. These are the geographical coordinates of the city block in question. So since we are dealing with California here, the latitude and longitude of various cities in California are captured in our data, and we are representing those itself. So as we can see that the longitude has a range somewhere between -126 and -122. So for a safer side, my Y limit, I'm setting it as -126, and my range is -126 to -112. So that is the X limit which I'm setting. We are using the two features in particular, latitude and longitude. So for longitude, we are having X, and for latitude, we are having Y. So Y limit to 32 and 43. Alright, now with these ranges set, by observing the maximum and minimum of the longitude and latitude, we are now going to have a scatter plot with several parameters. The first parameter is that of the validation data or the validation features which we have captured in validation examples, and the particular feature which we are using here is the longitude. Next, we have validation examples and the latitude feature of that. Now here we are going to have a color map of cool warm scheme, and the validation targets or the labels which I have to plot on the graph. I'm going to specify them here. Validation targets. We are predicting the median house value, and I'm going to divide this by the maximum from all the rows of the median house value so that my data is now normalized. Median house value, the maximum is accessed by the .max function like this. So as you can see, we have the title set to validation data. Now our X limit varies from -126 to -112. This we have performed scaling. So our map does not begin with 0, 0. It begins with -126, 32. And the Y limit is now 32 to 43, as you can see here. This is the function of the X limit and Y limit. Now the scatter plot, we have plotted the longitude and latitude examples using these features, and the targets or the labels are actually plotted here. The color scheme we have used is cool map, in cool warm, in the CMap or the CM which we had imported here. The CM library which we had imported here allows us to use this CMap function or the CMap attribute here in the cool warm scheme. As we can see here, there is a gradation from red to blue. Red indicates a high expensive price and blue indicates a relatively low price. This is the importance of this color scheme, which will help you visualize the data. You can see in the lower parts of California, you have a higher rate for houses. Now this was for our validation data. Similarly, I want to obtain a plot for my training data here adjacent to this. So again, we'll be calling the subplot function plt.subplot, and now here I want to fill the second column. So only the third argument will change to 2. I'm going to set the title to training data. Then similarly set the X limit and Y limit as we have set here. And again have a scatter plot with validation examples replaced by training examples and validation target replaced by training targets. Training examples again. We have training target again. Let's view this map. Cool. So as we can see here, the training data is the first 12,000 samples and the validation data is the next 5,000 samples. So here I want you to compare this with the real map of California and see if we have the training data and validation data together represent the entire map of California. It will be surprising to know that your validation set does not represent a real map of California. So why does this happen? The key thing to notice is that for any given feature or column, the distribution of values between the train and validation splits should be roughly equal. As discussed earlier, you cannot have a different distribution of data. For example, all of your summer data cannot be in the training and winter data in validation. The distribution of the training and testing and training and validation split should be equal roughly. So this shows that there is a fault in having a split like 12,000, 5,000 directly, since the distribution is not maintained. Like here you can see there is a lot of expensive prices here, but here relatively there is not much of a difference in the price. This is not a proper distribution, and the solution would be to randomize your training and validation splits. So we'll create a function to load the data into the TensorFlow model. Up till now, we have pre-processed the features and labels, split into training and validation data sets, and examined the data. Now we have found out that the split was not very correct. So we are going to define my own input function to load the data into the TensorFlow model by shuffling the training and validation splits. So let me define this function now. So the features I have passed here, this is going to be the data frame to create the splits. Targets are going to be our labels, median house value. Batch size is the size of inputs to be processed at one time. And shuffle is whether you have to randomize the data or not. So here we are going to keep it as true. Num epochs, the none value indicates that we are iterating infinitely on the data set for training. If I write 1, this means that the iterations are just going to be 1. Now we are going to convert the pandas data frame, which is features, into a dictionary of numpy arrays. So let's do that. My features data frame is going to get modified as we are first creating a dictionary of the features and accessing it using the items function. Now here we have a dictionary, so we would have key and value in this dictionary. And for each of these key and value, we are going to convert the value into a numpy array. So our key is going to be as it is, and our value, which is going to be written after this colon, key.array value for. So in summary, we have created a dictionary, we have accessed the key and value, and we have converted the value into a numpy array, and we have kept the key as it is. And now we are going to assign this whole thing into our features data frame. Now I'm going to introduce you to an API called dataset, which is a built-in TensorFlow API. So as you should know, feed-dict, which we have used earlier, is the slowest possible way to pass information to TensorFlow, and it should be avoided. The correct way to feed data to your models is to use an input pipeline to ensure that the GPU or your CPU never has to wait for data. So for this, we have a TensorFlow built-in API called dataset, which makes it easier to accomplish this task of providing a continuous flow of data to your CPU or GPU. So we are now constructing a dataset using the dataset API. Let's do that. We are going to store the value in a DS variable, and we are going to use the function from tensor slices features, targets. We are going to make a data set from the numpy array which we have created already. and we can set the batch size of our data using the batch function and pass this batch size as the parameter to this. And we are going to repeat it for num epochs value, which is already passed into our function. Now, if our shuffle is true, that is, if we are shuffling the data, which we are handling this condition here, and you're shuffling your data set using ds.shuffle function. Now, what my input function is going to return is the set of features and labels to be fed to our TensorFlow model. So we have created the data set, but we have no way of accessing this data, which is now in the form of a dataset TensorFlow. So that is why we use iterators. An iterator will give us the ability to iterate through the data set and retrieve the real values of data. There exist 4 types of iterators. We'll use the first and easiest iterator in our example, the one-shot iterator. The one-shot iterator can iterate once through a data set. You cannot feed any value to it. So how are we going to create the one-shot iterator? Using the DS object which we have created earlier. Make one-shot iterator. This is going to create the iterator, and to get the next element, as in Java collections you have hasNext or .next function. Here you have a getNext function. So we have created the iterator here, and we are returning the tensor that contains our data using the getNext function. Now this tensor is stored in our features, labels tuple. And now we are going to return these features and labels. So up until now, we have created a model to load the data into our TensorFlow. We have created a function to load the data into our TensorFlow model. Now, in the previous example, where we had used a single feature, we had a single feature to feed to the model. But now we have a lot of features, including synthetic features. So previously, we had simply converted the single feature into a numeric column. But in this example, we will have a function return a set of feature columns. So let's create a function to return a set of feature columns in the numeric column data format. Here we are going to pass a data frame containing the input features, and this function is going to return a set of feature columns in the form of a numeric column. So we are simply going to return a set of tf dot feature column dot numeric column. My feature is an iterator sort of functionality. Which we are using to iterate through your input features data frame. So each feature in input features is referred to as my feature. This my feature is converted to a numeric column using this function tf.feature.numeric column, and we are returning a set of these values. So now we have defined functions to load data into TensorFlow model, then created feature columns. Now we are going to create a training model. Finally, we are going to train our model based on the synthetic features which we have created, on the data set which we have obtained from these synthetic features, and the columns, numeric columns which we have created from this. So our data pre-processing part is finally over. We'll now move to training our model. So our train model is going to accept the learning rate, the steps required. The steps provide the number of passes back and forth through a single batch. We are again also mentioning a batch size. We are going to pass our training example based on which our model is going to get trained. Then the training labels, since this is a supervised learning problem. Validation examples and validation targets to fine-tune our model or to learn from the errors that our model is making. Now, in this function, we will proceed in 10 evenly divided periods so that we can observe the model improvement at each period. And at each period, we'll compute and graph the training loss. And because of this, we will be able to understand whether our model is converged or if it needs more iterations. So we'll also plot the feature weight and bias term values learned by the model over time. This is another way to see how our model converges. So to have these 10 iterations, I'm going to create a variable called periods and assign it a value 10 since we are running 10 iterations. Now I'm going to have a steps per period variable, which basically is how many steps in one period which we are taking. So that will be steps divided by a period. Now here we are using the TensorFlow's gradient descent optimizer function and clip gradients by norm function so that our model converges optimally using the TensorFlow API. The gradient descent optimizer accepts a parameter learning rate whose value we are passing as this learning rate, which we'll be receiving during the function call. And another thing is we are using the tf.estimator level API which is clip gradients by norm, and the first parameter is the optimizer and the next parameter is the limit or the range in which you want to limit your gradient to. This provides the limit to your learning model because sometimes it happens that your model escapes the values and your predicted value is very far away from your actual value. So to limit this jumping, we are clipping the gradients by norm by 5. Now we are going to use a linear regressor in TensorFlow which accepts feature inputs in the form of numeric columns and an optimizer. So this is where your training will actually take place. So let's create a variable linear regressor and call the API linear regressor with the camel case. And here we now, since this function accepts the input in the form of numeric columns, we need to pass this set of numeric columns because the create feature columns function takes input features and converts them into numeric columns. So we are going to call our create feature columns in the parameters of linear regressor. And we are going to pass the training examples to it since this is the data on which our model is going to get trained. And the second parameter is the optimizer, which linear regressor accepts. So now we are going to call input functions here because our model is ready. We want to now provide it the inputs to train our data. So using this, I'm going to create a variable training input function. Lambda is the keyword which we use for conditions. And here I'm going to call the my input function, which we had defined here to feed our data to the TensorFlow model. So we are now actually feeding the data to our TensorFlow model using the training example and training targets. The training targets has the value median house value which we are accessing, and the batch size is the batch size which is passed while calling our train model function. Similarly, we are having another variable predict training input function. And we are again calling the my input function which we have defined earlier with a batch size of 1. The first two parameters remain the same since we are now predicting the training output. Earlier, this was for training your model. You are feeding the data to train your model. So the batch size was something which would be passed here. Now we are predicting. Hence, for the prediction, we are going to have a single pass over the data so that our model does not learn this data. Hence, we are having a batch size of 1. We are not shuffling this data because in the end we are only using it for predictions. And the num epochs to be kept as 1. Now similarly, I'm going to have another variable for predict validation input. Again call my input function with validation examples. So we are having predictions being made on our training input as well as validation input. Right now we are dealing with validation input. So let's pass validation target median house value. Again shuffle equal to false and num epochs equal to 1 since we want to run it only for one iteration. Now we are going to monitor the root mean squared errors for training as well as validation. So I'm creating two lists, one for training RMSE and another for validation RMSE. So as and how we train our model during these 10 periods, we'll be able to see the changes in the RMSE. So I'm going to have a for loop running for 10 iterations. I range 0 to periods. Periods is 10 in this case. Now we are going to use the train function provided by the linear regressor API. I'm going to call it using the linear regressor object which we had created earlier. And it accepts two parameters which are input function. The input function takes in a tuple of the dataset. So the training input function which we have created here, which contains features comma labels tuple, which was returned by my input function. Features comma labels were returned by my input function as a tuple, which is stored in training input function. And we are now passing this tuple of dataset into our train function of linear regressor API. Training input function, and the second parameter is the steps. So the steps are going to be steps per period. Since we are running this for 10 iterations, in each iteration the number of steps will be steps by period. Now we are going to predict the values and store it in training prediction. Linear regressor dot predict function is used here. Again, our input function parameter accepts predict training input function as the value, which is again a tuple of the dataset. And this predict function returns a tensor of predictions, which is captured or caught in training predictions. Now, to access this tensor, we are going to convert it into a NumPy array. So we are going to have an item to iterate through the training predictions. And for each of these items, I'm going to access it as item prediction and the 0th element of it for item in this tensor. So here we are iterating the item in the training predictions tensor, and we are accessing it as the predictions column and the 0th entry in the predictions column and converting it into an array. And we are going to store this again in our training prediction variable. So we have basically converted our training predictions tensor into a NumPy array using these 2 lines of code. And since it is an array, we need to enclose it in another set of square brackets. Let's check if there are any syntax errors, which there are not. So let's do a similar procedure for our validation prediction. Again, we have linear regressor dot predict, and we have a predict validation input function. And similarly, we are again going to convert this tensor into a NumPy array for validation dataset also. Alright, now we are going to print the training and validation root mean squared errors. How are we going to do that? We are going to use the metrics that mean squared error function on training targets and training predictions, have a square root of that, and store it in the training root mean squared error variable. So first, let's call the metrics dot mean squared error function. With 2 parameters, training targets and training prediction. Since the root mean squared error is going to be in the form of your y and y dash. Y dash is the predictions your model makes. using all of these, using the predict function, and targets are your actual labels. So the mean squared error of these two, y and y cap, is calculated. Now we are going to have the square root of it using math.sqrt and enclose this inner thing into the math.sqrt. And now store it in a variable. So training root mean squared error. Similarly, your validation root mean squared error. So here we are training is going to get replaced by validation. Now we are going to print this so that we can monitor the errors, like for the period number and the RMSE with a precision of 2. Notice we are going to get 2 decimals after. So we are now going to print this, that for period 0, your RMSE was so and so with 2 decimals after the decimal point. And we are going to append the values to this list. Training RMSE.append. Why are we doing this? Because we want to plot the loss versus effect. RMSE.append training root mean squared error. Similarly, for validation RMSE, okay. Now we are going to plot. We have an error here. Let me check what it is. Looks like there's an invalid syntax. So there were a little bit of spelling mistakes in the append function. So let's move forward. We have now appended our training root mean squared error for each of the 10 periods within the training RMSE and validation RMSE respectively. Now we want to plot this data for all the 10 periods so we can monitor the change and the conversions in the errors over the 10 periods. So again, we'll be using matplotlib and we are setting the y label to RMSE. We are plotting RMSE versus the number of periods. That is RMSE in each of the 10 periods we are plotting on the graph. So our y is going to contain the RMSE and our x is going to contain the number of periods. So we are plotting the training RMSE on y and providing it the label training. Because we are plotting both the training RMSE and the validation RMSE in the same graph, we need to provide the labels so that when we visualize the data, it is visible along with the labels properly. I'm going to plot the RMSE with the label validation, and plt.legend is going to make these labels, training and validation, visible in the legend with the corresponding color code. And finally, our function train model is going to return a linear regressor object, which we have used to train and predict our data. Now, finally, we are going to call the train model after processing the data, feeding it to the model, and training and predicting on the training and validation. We are going to call this function. So what step we are at? We have done with the training our model. We are now going to call this training model, and it's going to return a linear regressor object. So let's catch it in a linear regressor variable. Call the train model function with a suitable learning rate. Now this learning rate you can modify and test it so as to get a variation in the RMSE values. We have kept these as parameters to be passed to the function so that they can only be modified here, and the performance of your model can be checked accordingly. Batch size we are going to provide as 5 currently. Training examples are the training examples which we have created earlier. Training targets are the training targets of the label of median house value. And then pass the validation examples and the target. Validation. So now we have called this function, and ideally we should be seeing the period number and the RMSE value, and then we are supposed to see a graph. While this runs, let us now evaluate our model. So we have trained our model on the training and validation sets. We now want to test our model on the untouched test data. So our test data is available at this particular location, California Housing Test.csv. So let me just capture the test features in So our model is now training. We just have to remember to keep the indentation in Python in mind. Our for loop ends here because after appending to the training RMSE and validation RMSE list, we are done with we have found these training RMSE and validation RMSE lists, and we are now plotting this cumulative list in the graph. So this should be outside the for loop. Now, while this is being done, let's prepare our test dataset in a similar manner. Test features. We want to add these synthetic features here also. So pre-process features and pass the test feature data here. And similarly, the test targets. Call with pre-process targets function and pass the test data set to it. Now, meanwhile, we can see that our model is done training. In the 0 period, the RMSE for training is 207 and it drops down to 161. If you recall, during the previous example, when we had used a single feature to predict the median house value, the RMSE was 180. You can see when we use more than one feature, our RMSE has reduced. That means our error has reduced and we have obtained a better accuracy of our model. Now the legend which I had mentioned in this code while plotting here, we had mentioned the labels for training and validation and they would be visible in the legend. You can see that our validation has been shown with a green line in the legend and training is with the blue line. This is the significance of the legend and the labels if you are plotting two graphs in a single plot. So after our training, we are now finally going to test our model. I have loaded it in the test features and processed the features and the targets as we have done for training and validation data. Now we are going to have test trainings input function variable, which is going to call my input function with test features and test labels or test targets the median house value shuffle false because in training we are only going to train and predict our model and check if it is giving the correct prediction or not. And naturally, we are going to run it for a single iteration so that our model does not learn this data. Similarly, we create a test prediction variable and call the linear regressor.predict function with the input function parameter passed as test trainings input, as we have seen a while ago while training our model. Test trainings input function, and we are now going to convert the data frame return or the tensor return into an array. Similarly, with the predictions column and the zeroth value for each item in the text prediction. So our brackets are now matching. Finally, our test RMSE is to be computed using math.sqrt metric.mean squared error and the two values are going to be test prediction and test targets as y and y cap. And we're finally going to print the RMSE or the root mean squared error obtained on the training data set to find out the accuracy. Test RMSE. So as we can see, the RMSE is 166, which is far lesser than the 180 which we had obtained when we had used a single feature to train our model. At the end, this brings us to the end of the demo. Let me just summarize what all we have done. We have pre-processed features and labels. We have created certain synthetic functions and also modified our labels by dividing each value by 1000. After this, we have split into the training and validation data sets. We have seen why you should randomize your data, training and validation before feeding it to the model. We have examined our data using subplots and matplotlib libraries. Then we have created functions to load data into the TensorFlow model, created feature columns which are accepted by the linear regressor API to train the model. And finally, we have evaluated the model on the test data set. So we hope that this has demonstrated how multiple features can improve your accuracy and how synthetic features can also improve the accuracy of your model. In case of any questions, do let us know in the comment section below. The description box contains the notebook which I have used for the demo right now. So you can go through it. In case of any doubts, be sure to mention in the comment section. We'll be more than happy to answer. Thank you for watching.